Hi everyone, welcome to the video. My name is Kazi and I'm going to talk about underwater wireless communications and a paper that we have published recently in IEEE Access about this topic. Now, as many of you may already know, IEEE Access is a Q1 journal and it has an impact factor of 3.367 as of 2020. On the right hand side of the screen you can see the first page of our paper. It's titled Green Underwater Wireless Communications Using Hybrid Optical-Acoustic Technologies. It's basically what the paper is all about. In this paper we have talked about how we can save energy by optimizing the choice of links between optical and acoustic technologies. So the background of the paper is really established on the fact that the underwater environment exhibits harsh conditions and they are very dynamic conditions which affect wireless communications adversely, and also the fact that underwater environment is extremely energy constrained. Now the premise is that with the recent emergence of autonomous underwater vehicles and remotely operated vehicles, the underwater communication networks are having to deal with high speed, high data rate technologies, and there have been many emerging applications that require these sorts of performance criteria, and therefore the underwater communication links need to have a quicker physical layer technology, and an optical communication technology underwater can provide just that. However, although underwater optics can provide higher data rates and they consume less power, the communication range that optics provides is short, and the links are not as reliable when the weather is unfavorable. On the other hand, traditional acoustics suffer from low data rate and high power consumption compared to optics. However, they can provide longer communication ranges as they have been used traditionally. Therefore, in our paper, we have combined these two technologies, optics and acoustics, together in a hybrid communication model, and that model reduces network power consumption while also meets the traffic demand for various applications and changing weather conditions. Before we jump into the details of the paper, I would like to talk about the contribution that our paper makes. To the best of our knowledge, our research in this paper is the first major work that studies power consumption implications for a hybrid optoacoustic communication network underwater. And it also incorporates the effects of traffic load and weather-dependent conditions in underwater network connectivity. The major contributions of the paper are as follows. We propose the hybrid optoacoustic underwater wireless communication network solution that optimizes network power and also considers both environmental variations and traffic demands, as we mentioned earlier. Also, our proposed model is a binary integer programming problem, and this has not been used before in the underwater network context. The other part of our contribution is that we solve this optimization problem and we compare it against we compare the hybrid solution and its performance against the performance of standalone all acoustic and all optical networks underwater, and we also compare it against a relevant work in the literature in terms of power consumption and throughput using simulation. Our results through the simulation show that the proposed solution, the hybrid solution, delivers significant power savings of up to 35% compared to existing solutions. Now let's jump into the paper. Okay, so this is the first page of our paper. As you can see, the title is the Green Underwater Wireless Communications Using Hybrid Optoacoustic Technologies, and all the author details are there, and this work was partly supported by the Department of Jobs, Tourism, Science and Innovation at the Defence Science Centre Australia under a grant provided by them, thanks to Defence Science Centre Australia. Now, In our abstract, we mention the background of our problem, and then we talk about how we have solved the problem and the results that we have received, and then we talk about the introduction in more details. I would like to grab your attention to the first figure, where it shows a common underwater wireless scenario, wireless communication network scenario. And this network, as you can see, has multiple nodes, and it has been segregated into 3 different network topologies. You can see in one of these topology there is a cluster, and the cluster includes some member nodes. This can be any communication network nodes or wireless sensor network nodes that collect data in the underwater and then pass on the data to the cluster head using optical links. These solid dotted lines are optical links because these nodes are closer together. And then there are AUVs and ROVs in the network, and then there are some relay nodes. And what happens is that the member nodes in all clusters, they collect data from the environment and pass it on to the cluster head. The cluster heads have dual communication links, multimodal links, either acoustic or optical, and they depending on the link conditions based on the weather and the traffic demand, they use either acoustic or optical links to pass on the data to the relay nodes or AUVs, or whichever is closer or suitable. And then the relay nodes forward this data, keep forwarding this data until it reaches the surface sink, and the surface sink then transmits the data to the nearby ground control or a ship station using radio frequency link. So this is basically the network scenario, and then let's move on to the next section, which is problem description. We have already talked about this, and then in the next section, section 3, we talk about the related works. As you can see from table 1, that all the related works, they have either talked about hybrid technologies or energy consideration or traffic variability or the dynamic environmental parameters. However, none of these works have taken into consideration all of these together as a whole, and therefore our proposed work stands out from all these relevant works. And then let's talk about the proposed system model, and it contains a network model and a traffic model. And I'm going to show you a figure which shows the network model, the simplified version. As you can see, it looks like very similar to the network scenario that we have seen in figure 1. It has clusters with member nodes and cluster heads linked with optical links, and then the cluster heads have either acoustic or optical links to forward the data to the suitable next hop node. And then once the data gets to the surface base station or ship station or the surface sink, it gets transmitted to the onshore control or satellites or whichever is required. So our problem is to gather the data from the member nodes, get it to cluster heads, and then the cluster heads need to make a decision based on the amount of data and the weather conditions, which link is the most appropriate link to forward the data with, either acoustic or optical, such that the network power consumption is minimized. In figure 2b, you can see a normalized underwater traffic load over a 24-hour period. As you can see that there is lots of variations in the traffic load, and around some hours of the day, for example from hours 15 to hours 19, for about 4 hours, the traffic peaks for some of them for some of the hours, and this is due to AUVs and ROVs joining in the network, and they require high data rate transmissions, and therefore the network traffic jumps and peaks during these hours. It's also important to mention that we have used weather data from two data sets. One of these data sets provide conditions such as the variation in salinity, temperature, pH in the water that affects acoustic communication to a large extent, and another data set has information about the water turbidity or the optical extinction coefficient that largely affects the underwater optical communication. In figure 3, you can see how these data vary within 6-day period. So these environmental variables have been used in our proposed hybrid optoacoustic solution. And the next part is developing an analytical model for both acoustic and optical communication networks. For acoustic communication, we have divided the entire analytical model into 3 parts: the channel propagation model, and then the noise model, and there is a power consumption model as well, but that's what we discuss in the next section, not in this section. However, we have done the same for optical model as well. For optical, we have derived, as you can see, a channel propagation model and an optical noise model as well. So these parameters affect communication links in several ways, and from these models we derive the power consumption model that's described in section 5 of the paper. As you can see, at first in 5a we derive the acoustic power consumption model based on the signal to noise ratio, and equation 27 shows the transmit power required for an acoustic link such that it can meet a target SNR given the acoustic propagation and the noise and the receiver bandwidth. We have done the same for optical power consumption as well. As you can see in equation 32, we have the optical transmit power that's required for a given target to meet a target SNR, and the optical noise comes into this equation as well, and also the optical channel propagation also comes into account. And then in section 5c we show how we derive the optimization, how we formulate the optimization problem. In the optimization problem, it should be noted that although it's a binary integer programming problem, from the network point of view, it can also be classified as analogous to a minimum network cost flow problem. It means we need to minimize the cost of the resources flowing through the network, and in our case the resources are data. And the other important thing to note here is that we introduce 2 binary decision variables, yi and xij, that represent the status power status of node I and link ij respectively. And using these 2 binary decision variables, we can switch on and off any nodes or links that are required for the data to be transmitted from a member node up to the sink at the surface of the water. Now, when basic premise is that when a node is not transmitting data, it should be switched off, and the corresponding link attached to the node should be switched off as well. And this is what saves power in the long run. And our optimization problem, as you can see here, from equation 37 with all the constraints from equation 38 to 44 are formulated such that only the nodes that are communicating for transmission of data are switched on for that specific period of time, and all the other nodes that are dormant remain in sleep mode, and they do not take part in communication, and thus it saves power. I'm going to talk briefly about the optimization problem. The objective function in equation 37 has two parts. The first part, the first summation, is actually the power consumption of all the nodes in the network, and the second part of the summation is the power consumption of all the links in the network. So when we minimize the total power consumption, we are actually minimizing the power consumption of all the nodes and all the links of the network. In the next page of our paper, we describe the algorithm that incorporates our optimization problem in minimizing the total network power consumption. As an input, it takes weather data and the traffic data that we showed before, and the output of this algorithm is the minimized network power consumption. As you can see, for each days 1 to 6 and for hourly traffic load and weather data, we calculate the network parameters for both acoustic and optical links, and then we compare the power consumption, and whichever power consumption is the lowest, we store that value and then use it for the optimization problem based on the constraints. So and then on table 2 we show what parameter values we used in our simulation. For results, as you can see, we have in figure 4 we have 6 days, day 1 to 6, and then we have power consumption, the power consumption metrics for 4 different scenarios. The first one is pure acoustic networks, which is indicated by the blue line. The green line indicates the pure optical network. The black line is a related hybrid solution from the literature, and our proposed hybrid solution is denoted by the red line. And as you can see, for all of these days, our proposed hybrid solution consumes the least amount of power. For day 3 and day 4, for some of the hours of the day, our proposed hybrid solution might consume a little bit more power, and that is because of several reasons, and we have discussed those reasons in our paper. But overall, on average, as you can see from figure 5, on average, our proposed hybrid solution can save power the most compared to all others, and on day 3 it can save up to 35% of power. In figure 6 we show the normalized mean offered load and the received load for the 4 different solutions over 6-day period, and as you can see, our proposed solution, that is denoted by the light blue line, is actually receiving the highest amount of load compared to all the other solutions. In figure 7 we show the received load percentage for each of these solutions, and as it's derived from the numbers in figure 6, and As you can see, our proposed hybrid solution in the dark blue line is always higher. In fact, it delivers about 84% of the load in day 5, and compared to all the other solutions, it provides higher delivery of data, indicating that although it minimizes power consumption, it does not, our proposed solution does not compromise on the amount of data that has been delivered. And this indicates that our proposed solution is quite a robust solution considering the variability of the weather conditions and the high traffic demands as well. In the last page of our paper, we have provided a table that summarizes all the results that we have obtained for our experiment, and then we conclude the paper by saying that our proposed strategy can save power by up to 23% compared to the standalone acoustic or optical solutions. The hybrid solution that we've proposed can deliver up to 35% more power savings compared to a related hybrid of acoustic solution that has been proposed in the literature. And we expect that this power saving technique is going to act as a significant driver for a green underwater wireless communication that paves the pathway for a green Internet of Underwater Things. Thank you very much for listening. Hope you enjoyed the video. I'm going to leave a link to our paper in the show notes, and please make sure that you take a look at the paper, and also leave any questions in the comment section, and I'll try my best to answer those as soon as possible. Thank you again.